Our goal in interval estimation is to use sample data in order to extrapolate and say, well, based on the sample that we've taken, we believe the true population mean or the true population proportion is between this lower bound and this upper bound with this percent confidence. So what this lecture is going to do is walk us through the process. Really, we're going to start out just trying to conceptually understand what's going on, and then we're going to walk through how the math is done. So we need to start with some definitions. First definition is a point estimate. It's a single number estimate of a population parameter. So if we want to try and find what the mean height is of somebody in our statistics class, we add up what all the total heights are, divide by how many people we have, and that mean is our point estimate. An unbiased estimator is a point estimate that does not consistently underestimate or overestimate the population parameter. So if we tried the same experiment, except now we just measured the 10 tallest people in the room, average their heights and use that as our estimate, that would be a biased parameter because we started by choosing the 10 tallest people. As long as we're randomly selecting them, it would be unbiased in that situation. An interval estimate is a range of possible values for a population parameter. So it's possible that after taking this sample of the 20 students that I have in my statistics class, I find that the average height is 5'7", and I further find that I'm 90% confident that the true average height of a Manor student is between 5'4" and 5'10". That 5'4" to 5'10" would be my interval estimate, the range of possible values for a population parameter. The level of confidence is the probability that the interval estimate contains the population parameter. Basically, for our purposes, we'll be looking at either 90% confidence, 95% confidence, or 99% confidence. And depending upon which of those three confidence levels we choose, it's going to change the math slightly. Specifically, it's going to change what constant we multiply by, based on the percent confident we want to be. The confidence interval is an interval estimate associated with a certain level of confidence. Really, what we're building towards in this lesson is being able to create these confidence intervals on our own. The margin of error is the largest possible distance from the point estimate that a confidence interval will cover. So what we're going to end up doing is calculating the margin of error, adding and subtracting by the margin of error to move that distance in either direction, and that's really what's going to create our intervals. So this is specific for a population mean. Later we're going to talk about a population proportion. When we're dealing with a confidence interval for the mean, we have to first calculate the standard error. So assuming that we know what the standard deviation is of the distribution, the margin of error is going to be equal to this special z alpha over 2 value that's specific to the level of confidence we want to achieve, times the given standard deviation over the root of n, the sample size. So really, we've seen sigma before, we've seen n. The sigma over root n is exactly what goes on bottom of our central limit theorem probability problems when we're calculating a z-score. The only thing that's kind of new is this z alpha over 2 idea. So what that really means is we're looking for a critical value based on the confidence level, where 1 minus alpha represents the confidence level. In other words, if we're trying to be 90% confidence, that would be 0.90 as a value of C. It would be represented by 1 minus 0.10. So in that case, alpha would be 0.10. If we want to be 95% confident, C would be 0.95, alpha would be 0.05. If we wanted to be 99% confident, C would be 0.99, alpha would be 0.01. So the idea is for each of these alpha levels, there's a particular Z value from the table which has that probability before it. So because you're going to have that 10% error when you have 90% confidence split between the right tail and the left tail, we're really looking for whatever that alpha value is divided by 2 to find a particular Z associated with that. Again, the standard deviation is the same as we've always used it before. The n, the sample size, is the same as we've used it before. But to expound on this Z alpha over 2 concept, this is what's really going on. Don't really worry about this wall of text. I'm going to explain it best I can. But basically, if we want to be 90% confident, that means we want the 90% of values closest to the mean. That leaves out 10% of values, specifically the 5% on the highest end of the range and the 5% on the lowest end of the range. So essentially what this paragraph is showing is how we get to that 0.05. We take what starts as 100% minus the confidence level expressed as a decimal. So in this case we want to be 90% confident. Expressing that as a decimal is 0.90. So when we do 100% minus 0.90, we get 0.10, or 10% as our total alpha. So that 10% represents what should be in both of these two shaded areas together. Because we really only want to deal with one of the two shaded areas when finding the z that corresponds to it, we're going to divide that 10% by 2. If we divide 0.10 by 2, we get 0.05. 0.05 represents alpha over 2. So now we're trying to find the z-score that has 0.05 in front of it. The same way that we did in the second lesson on the normal distribution, where we start in the middle of the table to find a specific percentile, we're trying to find where 0.0500 occurs in the table. If you look through the table and look for it, it's happening somewhere between negative 1.65, which is 0.0495, and negative 1.64, which is 0.0505. Really, it's happening right in the middle of those two. That's where we're getting this value, z equals negative 1.645, is having exactly 5% to the left of it. Again, we're basically finding the 5th percentile the same way we did in the previous unit. This side really represents the 95th percentile because you have this 90% unshaded plus this 5% shaded to the left of the value. But because the table's symmetric, we know that if this side gave us negative 1.645, this side's going to give us positive 1.645. So basically, z alpha over 2 is 1.645. When it goes into the formula, we're going to add and subtract it. So the sign really isn't as important, but it's easier to calculate by looking at the left side and finding the negative value first. The good news is you don't really have to do all this graphical math. The reason you don't have to do it is because there's only 3 basic values you need to know. Specifically, you need to know that when we have 90% confidence, you're going to use a z alpha over 2 value of 1.645. When we have 95% confidence, you're going to use a z alpha over 2 value of 1.96. And when you have 99% confidence, you're going to use a z alpha over 2 value of 2.575. So you definitely don't need to have these memorized. You can just write them down anywhere in your notes and refer back to them. But you're going to be using them often enough that they're going to start to become second nature to you. These 3 numbers are going to come up a lot in the remainder of this class. When I want to calculate the margin of error for a given situation, remember the margin of error equals z alpha over 2 times sigma over the root of n. So in this case, we start by saying, all right, if confidence level is 0.90, what z alpha over 2 value is associated with that? I look up in my notes and find that for 90%, that's the one we just showed graphically, it's 1.645. So this calculation becomes 1.645 times sigma, which is 6, divided by the root of n. In this case, n is 45. I set up the next 2 the same way, except making sure that I look up the specific value from my notes for this confidence level. So really for number 2, since confidence level is 0.95, we use a z alpha 2 over 2 value of 1.96. That 1.96 gets multiplied by 4 divided by the root of 100. For the final one, number 3 here, since we have a confidence level of 0.99, I look up in my notes and see that that goes with a z alpha over 2 value of 2.575, and I multiply 2.575 times 1.2 divided by the root of 80. Here's how all that math looks done out. 1.645 times 6 over the root of 45 gives me a margin of error of 1.471. The margin of error for the second problem turned out to be 0.784, and the margin of error for the third problem turned out to be 0.345. So the general idea here is these margins of errors tell us how much to move off of the mean, both to the left and to the right. We calculate the margin of error first, then we create the confidence interval using that margin of error. So when we go to create the confidence interval, we take the mean minus that margin of error we just calculated, and that's in front of the comma, the lower bound of the confidence interval. Then we take the mean plus that error formula that we calculated, and that's the upper bound, the upper limit that comes after the comma in the confidence interval. The result should be displayed as lower limit, comma, upper limit, where the lower limit's always smaller than the upper limit. So let's say we were looking to find out the average amount of money that Mr. Moulton spends on his family when he gets dinner for everyone at Chick-fil-A. I could do a confidence interval based on the mean amount that I found, and the confidence interval might end up saying that the lower limit is $25 and the upper limit is $39. That would say that we're 90% sure the true average amount that I spend on a meal for my family at Chick-fil-A is somewhere between $25 and $39. Always the smaller number has to come first, the larger number has to come second. So that interval would be displayed as parentheses 25, comma, 39, and parentheses. If we do these confidence intervals for these same situations that we had before, we have what the margin of error is that we previously calculated. All we're going to need to do is take the new piece of information, which is x bar for each of these, or the average from the sample, and we're going to first subtract the margin of error that we calculated, then add the margin of error that we calculated. So if 20 is the mean and we previously calculated the margin of error as 1.471, to find the lower bound we do 20 minus 1.471. That gets me to 18.529. To find the upper bound we do 20 plus 1.471. That gets me to 21.471. Again, we're just taking the work that we did previously to find the margin of error, where we did z alpha over 2 times sigma over root n, and we're taking the given mean, first subtracting it, then adding it. When we do it for the second situation, we're taking the given mean of 150, first subtracting 0.784, then adding 0.784. That gets us to our confidence interval. We're 95% sure the true population value lies between 149.216 and 150.784. For the final situation, we take the mean of 10, we add and subtract the margin of error of 0.345. That's how we get to a lower bound of 9.655 and an upper bound of 10.345. This is the way they might look as word problems. So the first word problem says an IT company wants to estimate how much revenue they bring in for each new client that signs up for their services. A simple random sample of 41 clients had a mean revenue of $2,500. Construct and interpret a 95% confidence interval for the mean amount of revenue the new client brings into the company. Assume the population standard deviation is known to be $500. In this case, we want to start by picking out the key pieces of information they've given us and label what they should be for the problem. So the first number I see is this 41 clients. 41 clients is my sample size. I should label it N. N equals 41. The next thing I see is a mean revenue of $2,500. 2,500 is my X bar, the sample mean. Next thing I see is a 95% confidence interval. I should write that in my notes for the problem as C equals 0.95, but I might even want to do the next step, which is to find the Z alpha over 2 associated with it. When I look back to 95% confidence, I should see a Z over alpha over 2 value of 1.96. So I'm already associating 0.95 confidence with 1.96 Z alpha over 2. Finally, I see this $500 as the known standard deviation. I'm going to put that in as sigma for the standard deviation. I can now construct my margin of error calculation as the Z alpha over 2 value, 1.96, times the standard deviation, given as 500, over the root of n, in this case the root of 41. Only after doing that margin of error calculation do I want to involve the sample mean of 2500. I want to take that sample mean, subtract the margin of error, take the sample mean, add the margin of error. Separate them by a comma, and that's going to be my confidence interval. For the second situation, I have a random sample from 35 years of 18 women trying out as the mean number who try out for Manor's basketball team. That 35 years is my n, or the sample size that I'm looking at. The mean of 18 is my x bar, or the thing that I'm going to add and subtract from. It says I want 99% confidence. I associate 0.99 confidence with 2.575 as a z alpha over 2 value. Finally, I'm given the standard deviation of 5. So here's the way these calculations would look. For the first one, I calculate margin of error as 1.96 times 500 over root 41, which is 153.05. If I then take the given population mean and subtract, then add, I get a final confidence interval of 2346.95 to 2653.05. So the true population mean amount that a new customer brings into this company, we're 95% sure it lies between these two numbers. Similarly, when we do the Manor Athletics example for women's basketball, we get a margin of error of 2.176. Our confidence interval then takes the mean, 18 minus 2.176, 18 plus 2.176. So we find that the true population average, if we were to look at hundreds of years of Manor basketball, should be between 15.824 girls trying out and 20.176 girls trying out. This is a skill that takes time to master for sure. I would say that the more practice you can get with these, you definitely want to try the crossword problems, try the homework. But basically, once you get down the steps to this, once you get down how to pull out what the specific variables you need are and how they're presented, it's really just getting used to putting in your calculator, setting up the intervals the right way, and following the formula. Now that we've learned how to estimate means, we need to learn a similar and slightly more difficult way to estimate proportions. So proportions are really binomial situations where I have a yes or no question, I have success or failure, and in these cases we're going to be estimating proportions with similar type formulas to how we did z-scores for proportions in section 7.5. So the idea is that when we find the margin of error for this situation, we still use a z alpha over 2 value that works the same way that it did before. For 90%, it's 1.645. For 95%, it's 1.96. For 99%, it's 2.575. We then are multiplying by the exact same thing that we used to divide our z-scores for proportions. The square root of p hat times 1 minus p hat over n. Remember that p hat is the sample proportion represented by x over n, where x is the number of people who fit the trait we're looking for, and n is the total number of people in the sample. So, this extra thing that's written up here that says we want to make sure it's large enough that np is greater than or equal to 5 and n1 minus p is greater than or equal to 5 basically just means that we need to have a large enough sample size to validate the central limit theorems used to apply the normal distribution. This was the same criteria that was used when we were doing z-scores for proportions. So here's the situation. Basically, the first thing we have to do is calculate p hat. The way we do that is x divided by n. So 37 divided by 100 gives me 0.37. I'd want to write down p hat equals 0.37. I'm going to warn you that a lot of times I think I round these to 2 decimals, whereas in Cengage they wouldn't be rounding these at all. So you're actually better off when you're doing these problems in the online system, not rounding these numbers as you go. That said, 37 to 100 does work out to exactly 0.37. Now that I have my p hat, I can apply the formula by finding what value goes along with 0.90 as a confidence level. That value is or I'm sorry, not 2, 1.645. So I take 1.645 times the square root of 0.37 times 1 minus 0.37 over the n of 100. The key here is to make sure all of that stays under the square root by using proper parentheses. Similarly, for the second question, I'd first do 15 over 75 to get my p-hat. I'd then convert the confidence level of 0.95 to a z alpha over 2 value of 1.96. And I'd set this up as 1.96 times the root of, really this would give me, I believe, 0.2 times 1 minus 0.2 over 75, all under the square root. The final problem, I would start by doing 180 over 225. I would use that in order to get a p-hat value. I'd then say the confidence level 0.99 should point me to 2.575 as a z alpha over 2. I'd do 2.575 times the root of p-hat 1 minus p-hat over 225. Here's how all that math would look. Here I calculate p-hat as 0.37. I calculate the margin of error as 1.645 times the root of 0.37, 1 minus 0.37 over 100, and that gives me a margin of error of 0.0794. For the second problem, after setting up and solving, I get a margin of error of 0.0905, and for the third problem, I get a margin of error of 0.0687. Same way that we use that margin of error when we were calculating confidence intervals for means, we're going to use that margin of error to add and subtract from the sample proportion to create my confidence level for proportions. So essentially, the p-hat that we calculate minus margin of error is the lower bound, p-hat plus margin of error is the upper bound. So we've previously calculated p-hat as 0.37, we previously calculated the error, we're just going to add and subtract the error here. For the first one, 0.37 minus the error that was calculated as 0.0794, 0.37 plus the error that was calculated as 0.0794 gives me a final answer of 0.2906 to 0.4494. So in this situation, we're 90% confident the true population proportion is between 29% and about 45% based on getting 37% in our sample. Want to note here, we just had a big election. This is how election polling works. Whenever you saw something on CNN or some other news source that said Joe Biden is currently polling as getting 53% of the vote in Pennsylvania with a margin of error of plus or minus 4%, that was literally a confidence interval. It would be a confidence interval that said lower bound 49%, upper bound 57%, because it was centered at 53 with a margin of error of plus or minus 4%. So these confidence intervals are very useful and actually very commonly used in a variety of fields. I would say that politics is definitely one where you see them often, but there's all sorts of customer surveys that are used in various businesses. There's a variety of ways that confidence intervals can guide decisions. Continuing on, going over what we get here, when we do number 2, we're taking the p-hat of 0.2, adding and subtracting the margin of error of 0.0905. That's how we get the final confidence interval of 0.1095 to 0.2905. For the final problem, we get a confidence interval of 0.7313 to 0.8687. We're now going to try a couple word problems involving these percentage confidence intervals. Again, the key thing to do is to pull out the information as it was presented on the previous slide examples so that you can translate from word problem into math problem, then you follow the same mathematical principles. So in number 1, a political candidate wants to estimate what percent of the vote they will get in the upcoming election. A simple random sample of 140 likely voters found 82 said they would vote for the candidate. Construct and interpret a 99% confidence interval for the proportion of voters who will vote for the candidate. So the first things I have to pull out are N, X, and confidence. N is the number of people in the sample, 140. X is the number that fit what we were looking for, 82. C is the level of confidence I want, in this case 99% is 0.99. So the first thing I need to do is take X over N to find p-hat. 82 divided by 140 in my calculator will tell me that p hat. Then I need to convert the confidence level, c equals 0.99, to a z over alpha over 2 value. 0.99 is associated with a z alpha over 2 of 2.575. So my calculation becomes 2.575 times the root of parentheses p hat that I got from 82 over 140 times 1 minus that same p hat all over 140. Make sure it's all happening under the square root. After calculating that margin of error, I would add and subtract it from the p hat that I calculated to find the lower bound and the upper bound of the interval. For the final problem, here I have 30 of 78 to calculate my p hat. Since I have a confidence of 90% or 0.90, I'd use a z alpha over 2 value of 1.645. Again, I'd set up 1.645 times the root of parentheses p hat found by 30 over 78 times 1 minus p hat all over 78, making sure it's all happening under the root. Here's the results of that math. When I do the political candidates margin of error here, I get 0.107 margin of error. That means that I have him polling at between 48 and about 70% of the vote. Would be great to hear as a candidate, but really this means that I can't say I'm 99% confident to win the election. To win the election, I'd have to get more than 50%, and it's still possible that I get less than 50% here. If you're ever worried that the margin of error is too high, like you would never see on CNN them reporting a poll with a margin of error plus or minus 11%, that's really not accurate enough. The reason is because the sample size wasn't big enough. If you increase the sample size to be much larger, that's one of the best ways to cut down on your margin of error. For this random sample of Manor students where we're trying to figure out what proportion can speak a second language other than English, we found from our sample that it was 38% or 0.38. When we then calculated the margin of error of 0.0904, we added and subtracted it from 0.38 to get a final confidence interval of 0.2896 or about 29% to 0.4704 or about 47%. So based on our sample where 38% of the students could speak a second language, we estimate with 90% confidence that the true proportion of Manor students that can speak a second language is between 29 and 47%.